Last time, we looked at a model for an oscillator that's just capturing the phase of the oscillation and not its amplitude. And we looked specifically at uniform oscillation where the speed is constant as we go around the circle as one example. And today, in this video, I'm going to talk more about the non-uniform case, where as we go around the circle, we might go very slowly for some part of it, faster, very fast through some part of it, and then more slowly again. And so here's an example of that. If we have d theta dt, so the angular velocity, equal to r minus cosine theta, well, that curve gives us a large velocity at some points, namely near pi or negative pi, and a smaller velocity at other points, namely near 0. So we expect to be moving very fast when we're along this part of the cosine curve, and we expect to be moving much more slowly when we're along this part. And so that's been drawn here with a double arrow for where we're moving quickly when our angle is over near pi or negative pi, and a single arrow for where we're moving slowly when our angle is near 0. We were making this description in the case where r is bigger than 1, and there are no fixed points. And that's important because if we had fixed points, we wouldn't be able to go all the way around the circle. We would get stuck at a stable fixed point, or we would get stuck at a half stable fixed point. And so what happens as r approaches 1? Because as r approaches 1, we're going to be approaching this case where we have this half stable fixed point, and we're going to always land stuck right here, approaching 0 from below. So we expect things to change pretty continuously, and so when we are in this case where the bifurcation is just happening, it basically takes an infinite amount of time to get around the circle. Like, we never get around the circle. But just a little before that, r is a little bit bigger than 1, and we do get around the circle, but that slowness that occurs because r is really close to 1 and we're really close to the bifurcation should manifest in some way. And so we expect there to be a slow region that's sort of actually like a remnant of the existence of the bifurcation. So when r is 1, we have the fixed point, and if r is a little bit bigger than 1, we have this slow region. And as r gets bigger and bigger, that slow region gets less and less slow. And so this slow region, the slowness of that region, should have something to do with r. So here's a question. Can we use the period of the oscillator, how long it takes to get all the way around, as kind of a sign of how close we are to the bifurcation? Since once we hit the bifurcation, it's actually going to take an infinite amount of time to get all the way around. And so when we're really close to the bifurcation, it should take a really long time, and when we're further, it should take less time. And so how long does it take to get around? The time will be the integral of little time increments dt over the time that it takes, and those time increments dt can be rewritten this way, dt d theta d theta. So as theta ranges from 0 to 2 pi, this is adding up the amount of time that we spend going through small increments d theta. So this is the problem we're interested in, how long it takes to go around the circle associated with this velocity. But actually, instead of solving this problem directly, let's consider a pretty closely related problem, which has this same saddle node bifurcation structure. And let's consider the problem. We just have the classic normal form for the saddle node, r plus x squared. And so instead of trying to go around the circle, we're going to go from all the way from negative infinity to positive infinity. And I just want to note that when we're pretty far out this way, we're moving incredibly fast. And so we spend very little time on that part of our trajectory, and we also spend very little time on this part of our trajectory. And so pretty much all the time is spent getting through this bottleneck that is basically kind of a ghost of being near a bifurcation. And so when we take this integral, the time in the bottleneck is what's going to dominate. And so let's see, we want to add up the little pieces of time per increments dx over all the increments dx. And so this is dt dx, which is 1 over dx dt. And so that's 1 over dx dt, which is r plus x squared for this curve dx. And so we're going to integrate this. But actually we're not going to integrate this. The thing that we care about is how this depends on our closeness to the bifurcation, because the question we were asking was, does the amount of time it takes scale with how close we are to the bifurcation? And so to answer that, we don't actually need to figure out exactly what this integral is. We just want to know, does this scale with r? And if it does, how will it scale with r? So I'm going to do, I guess, basically a little bit of manipulation. First of all, I'm going to pull this r out from the equation. And so I get a 1 over r and a 1 plus x squared over r. So that was r over r gave me the 1, and this x squared over r. These things are completely equivalent. And now, okay, x squared over r is pretty suggestive of a u substitution. So I'm just going to do the u substitution that it suggests. I'm going to let u equal x over the square root of r. And that tells me that du is dx over the square root of r. So then dx is equal to the square root of r du. So I substitute in square root of r du where there was a dx. And I substitute in u squared for x squared over r. Okay, and so this is now what the integral is equal to, 1 over r, square root of r du over 1 plus u squared. And I'm going to pull out all the r stuff. Okay, so we have 1 plus the square root of r times the integral from negative infinity to infinity of du over 1 plus u squared. I want to note that inside this integral, there are no r's. So this integral is just going to give us some number, some constant. It could be 7 or 5 or 13. I don't really care, because the thing I was interested in was how this stuff scaled with r. And that scaling with r has been pulled out of the integral, and it's a 1 over square root of r scaling. So it happens to be the case that this integral integrates to pi, and there's some trigonometric substitution that would allow you to see that. But what I really cared about was this 1 over square root of r scaling on the amount of time it takes to get through that bottleneck. So the differential equation we were considering was x dot equals r plus x squared, and we found that the time scales as 1 over the square root of r for r close to 0. Those are the values of r that we care about, and those are the values of r where things really take a long time through the bottleneck. And so this is what that curve looks like. Here's r, and here's the amount of time it will take to get through the bottleneck, and it diverges as we approach r equals 0, as you can see from the form of this equation, and so it's just going up like that. And we expect that. It should go to infinity as r goes to 0, since at the exact point where r hits 0 in this formulation, there's going to be a fixed point, and we're going to get stuck at the fixed point instead of actually being able to traverse from negative infinity to infinity in x. And so, okay, it'll take an infinite amount of time to get through because we never actually get through. So in this way, we can see that we really can see our closeness to the bifurcation in how slowly x is moving. The original thing we cared about was theta dot equals r minus cosine theta, and it's going to behave pretty similarly. Let's look at that. So it has a parabolic shape near theta equals 0, and so I'm just going to do a little bit of a Taylor expansion right there, taking the first two terms. I think these are right. And so what you can see is that I have a constant plus theta squared over 2. Well, that's basically constant plus x squared. These are really similar in form. And so I expect time to go as 1 over the square root of r minus 1. There could be a factor of like 2 in there or something, but I don't care about constant factors. The thing I want to know about is the dependence on r, and you can see that we still have that square root dependence. So that means that as we go around an oscillator, and we're going through a slow period and a fast period, the total time that we take, we're assuming it's really determined by how much time it takes to get through this bottleneck. And this bottleneck, the amount of time it takes to get through there is proportional to how close we are, 1 over the square root of how close we are to the bifurcation.